From the moment you emerged screaming into the world, the complex network of neurons that we call your brain began to learn. Through the input of your 5 senses of touch, sight, hearing, smell, and taste, you immediately began your lifelong journey of recognizing patterns and creating connections between inputs. And it's these connections you form that then inform your outputs, such as your thoughts, speech, actions, and emotions. But say we wanted to replicate something like this learning process in a computer. Well, it's this line of thinking that led to one of the fundamental building blocks that make AI possible, and that is the idea of an artificial neural network. A neural network can be described as a connected series of algorithms that are designed to identify the relationships in a set of data, modeled after the way a human brain works. Your body has a vast amount of sensory inputs that send signals throughout a network of neurons in your brain that then trigger specific outputs in you that are defined by all the connections your neurons have created based on the inputs you have received throughout your life. Only while your brain came pre-packaged and ready for input to start learning, we need to build the neural networks that make an AI. And to do that, we use computers and a whole lot of math. So in today's episode, that's what we'll begin to break down by exploring just what exactly is a neural network and the process of how it works. One of the classic examples when it comes to explaining the basic idea of how neural networks function is training an AI to recognize handwritten numbers. We will do this by inputting a large set of grayscale images of handwritten numbers between 0 and 9, and our desired output will be a number between 0 and 9. So a simple example of training this kind of network successfully would be that when we input an image of an 8, it will output an 8. To train a neural network, firstly, we need a large amount of training data. So for example, if we were training a network to recognize clowns, we'd need a terrifying dataset of thousands of clown pictures. The reason training an AI to recognize handwritten numbers is such a common example is because there is a readily available dataset to do this, called the MNIST database, that has 60,000 images of handwritten numbers already pre-prepared, each formatted to be a 28 by 28 pixel square in black and white. So to build our neural network, let's start with what our inputs will be, which will be 28 by 28 pixel images. Now, as we discussed in our episode on binary, a computer doesn't actually see an image. It processes it left to right, top to bottom, 1 pixel at a time, processing each pixel as a binary piece of data. That means our network will be starting with 28 by 28 input neurons called nodes, which is a total of 784, one for each pixel. And our output will be a number between 0 and 9, so that means we have 10 output nodes. So what goes in the middle between these? These are what are called the hidden layers. Now keep in mind, this imagery and words we're using here are just symbols to help visualize what is actually just a whole lot of code, which is the programming language that tells computers how and when to run its functions. In reality, a neural network looks a lot more like this. But back to the mysteriously named hidden layers. We have our input layer, which is our input nodes. We have our output layer, which is our output nodes. And we can then have one or more layers between these. These in-between layers are called the hidden layers because we don't dictate or see what they do. We know what our inputs are and we see our outputs, but we don't see what these middle neurons are doing. Maybe think of it a bit like burning your hand on something hot, and you pull your hand back. The input was the hot kettle, the output was you pulled your hand back. You know these two things, but you have no idea what neurons fired in between that brought that result. But we do know it was the correct result. That is a massive oversimplification of how the brain and neurons actually work, but you get the point. The number of these hidden layers you have is completely up to you, and the optimal number is a topic of great discussion, as more nodes and layers does not necessarily lead to better or more accurate results. Though the upper limit of the number of nodes you can have will be largely decided for you by the processing power of your system. For this example, let's say we have 2 hidden layers of 8 nodes each. Now every one of these 784 input nodes will be connected to every one of those 8 nodes in the first hidden layer. Then every one of those nodes will be connected to the next 8 nodes in the second hidden layer, and then the same to the output nodes. So just in the journey from the input layer to the first hidden layer, we have 6,272 connections, which starts to give you an idea of just how much computing power can be involved in a large neural network. So now we have all these lovely nodes, but what even are they? Well, each node is basically a mathematical function that outputs a number between 0 and 1. And this number is passed on to each of the nodes it's connected to, and they then include that number in their mathematical functions that produce a number between 0 and 1. Now our old friend 0 and 1 should be familiar to us from binary, where 1 was on and 0 was off, and that's a similar way we can think of it here. We can describe a neuron with a value closer to 1 as being more active, and a value closer to 0 as being less active. And what connects each of these neurons is even more maths, which should come as no surprise when we remember that at their most fundamental level, computers are always just processing a whole lot of numbers. Now let's jump back to our input nodes and see if we can walk through how this process works. At our input, we have a 28 pixel by 28 pixel black and white image of a handwritten number. Now each pixel is converted into a brightness value between 0 and 1, which becomes the values for each of our input nodes. So what now? Well, now we get to discuss weights and biases. First, let's tackle weights. As part of the math functions that build this network, each node is assigned a weight, this being a number value that tells the network how important that particular node is. A higher weight value means that node is more important, a lower value, less important. Now, as a simple theoretical example, the input node associated with the pixel in the top left corner could end up with a very low weight value after training, as it plays little role in determining the shape of any of the numbers, whereas pixels towards the middle may end up with a higher weight value. So now let's cover the bias, which is once again another number assigned to the math function for each node, but the bias can be thought of as a threshold that must be crossed before the node will activate and pass on its data. For example, you could have a bias that says, until this neuron passes a value of 0.7, it won't activate. So it's these weights and biases that play the largest role in whether or not a neural network will produce the correct answers, as it is these numbers that are adjusted as we train the network so that it begins to recognize what data is important and what is not. So as we input our first piece of data into the network, these weights and biases will be set to mostly arbitrary numbers, as the network hasn't learned yet which parts of the data are important, or what to do with it. So our data will travel through the various nodes, and in our output nodes for numbers 0 to 9, we will end up with a range of values between 0 and 1. What we're looking to end up with is a high value closer to 1 in the correct output node, and low numbers closer to 0 in all the others. But first time round, these values are going to be all over the place, because we haven't done any training yet. So what's the process of training look like? Well, as part of setting up the neural network, we set it to calculate as part of its output a value called the cost value, and this is a number that measures how accurate the output is. The higher the cost value, the less accurate the answer, as it tallies up the totals in the incorrect outputs. So training the network becomes centered around achieving one simple goal: lower the cost value. And it does this through a process called backpropagation, whereby the network works backwards through its nodes, adjusting the weights and biases to lower the cost value. It does this through a method kind of like finding your way down a hill in the dark. You take one little step in one direction and see if you move down or up. If you move down, you take another little step in the same direction, until no matter which direction you step, you're not getting any lower. Now mathematically, it's much more complicated than this, and a lot more involved, but this is the basic idea of the process. The weights and biases are incrementally adjusted until the lowest cost value it can calculate with the given dataset is in place. But then we repeat this thousands and thousands of times with new input data, and the network slowly builds up in its weights and biases its own set of rules in the hidden layers for how to correctly identify the numbers. This is why it's called machine learning, because we never specifically give the computer any instructions on how to identify individual numbers. It builds its own set of rules based off of the data we input and the feedback we give it through the cost function. In the hidden layers is a whole lot of connections between data that we wouldn't understand at all, but it does give the correct output. We have in our own mind our own set of rules for what makes a 3 identifiably a 3, and so does the network by the time training is complete. But does it actually know what number it's looking at? Nope, not even close. While the output may be correct, it's just balancing its numbers to give the lowest cost value. You can input an image of complete noise into a trained network like this, and it will tell you with great certainty that it is a particular number. And if you input into this an image that is a series of numbers in one image, its accuracy will once again drop. Because the neural network doesn't now recognize numbers in the sense that we do. It's just outputting a number in response to the input numbers that is defined by weights and biases set in the training. Now, this was a very, very basic example. Things get way more complex than this, and even the actual math involved in this simple network is staggering. The internet age and the incredible speed of our current processors is what has made the modern AI era possible, because it has given us access to vast networks holding incredible amounts of data, and the computing power to be able to actually process that data. But an AI's output will always reflect the data it is trained on, much the same as a human child. If you tell a child that the colour red is called blue, and never let them learn otherwise, they will spend their lives incorrectly saying that red is blue. And if you train an AI with images of fish but label them as dogs, then ask it to generate an image of a dog, you will be given an image of a fish every time. This is why it's vital we pay close attention to what exact data we are using to train AIs, and it's also vital to remember that while an AI may be able to generate you a photo of a dog catching a ball, it has no idea what a dog or a ball actually is. And that's where we'll be heading next time, as from here we'll start to talk about image generators, and then large language models like ChatGPT that are changing how we communicate and how we work every day.